Hey everybody, my name is Tam N. I'm a tutor here at Chegg, and today I'm going to be talking about the Nand and Nor logic gates. So before I start talking about the Nand and Nor logic gates, it's important to know what the and or logic gates are, because after all, they are the fundamentals of digital logic. And the Nand and the Nor gates are simply created from the and Nor gates. So let's take a look at the AND gate. You guys are probably familiar with that. If we have two signals A and B, then the output signal Y is only one if A and B are 1. If and only if A and B are 1. So the NAND gate, all it is it's an inverted AND gate. It's as if you put an AND gate and then an inverter right after the AND gate, right on its output. So that means the NAND gate, the truth table, it's going to have zeros where the AND gate should have ones, and ones where the AND gate should have zeros on the outputs. So that means the NAND gate is always 1, it always outputs 1, unless the A and B signals are both 1. Right? So if A and B are both 1, then Y is 0. Everything else, Y will be 1. The NOR gate is similar to the NAND gate in the sense that it is simply an OR gate with an inverter tied to the output. So over here we have an OR gate. So an OR gate, its output is only true, only 1, if there is a 1 in its inputs. So it doesn't matter where the 1 comes from. It can come from A or B or even both A and B. Right, so for the OR gate, we have it's always going to be 1 unless A and B are 0. So the NOR gate, logically, it will only have a 1 when A and B are both 0. Everywhere else, it's going to be 0. If there's a 1 in the inputs, the output's going to be 0. Right, and the symbol for the NAND gate is simply an AND gate with a circle at its output. Right where the output is, there's a circle. And for the NOR gate, it's the same as an OR gate, but there's a circle right where the output should be. And it's not very creative, but I'm not the one who made these drawings up. It's just the way it is. But the bright side is it's very easy to remember. You're not going to forget which one's a NAND gate, which one's an OR gate. It's just the one with the circle. Alright, so let's go ahead and do a sample problem. Suppose I have a logic circuit like so, constructed of NAND, 2 NAND gates and a NOR gate, and it's wired like so. I want to find the output Y, alright, and this is Y. So let's go ahead and do that step by step. Here we have a NAND gate, and its inputs are 1 and 0, right? So a NAND gate, you can just think of it as an AND. Think what an AND gate would do and then invert that. So if an AND gate took a 1 and a 0, it would output 0, right? Because 1 and 0 makes 0. But this is an AND gate, so you do the opposite. It's going to output a 1. You're going to do the same thing with the NOR gate. We have a 1 going into the NOR gate and a 0 going into the NOR gate. Okay, usually, if you have that into an OR gate, it would output 1. But this is the NOR gate. It's the opposite. It's going to output a 0. So this final NAND gate, we have a 1 going to the NAND gate and a 0 going to the NAND gate. Doesn't that look familiar? It's the same thing. It's the same thing as this one. It's going to output a 1, right? So your Y is going to equal 1. Something interesting about the NAND and NOR gates that a lot of people don't realize at first because it's not very intuitive. But the NAND and NOR gates are what we call universal gates. And I'll prove that with a NAND gate. What a universal gate means is that you can create all logic gates with that gate. Alright? So you probably think you misheard me, but you didn't. You can create all logic gates using just a NAND gate, and also a NOR gate. Or a NOR gate. So let me prove it to you, because I'm almost positive you don't believe me. Using only NAND gates, I am going to create the AND gate, the NOT gate, and the OR gate. Okay, and we know AND, NOT, and OR creates the universal set for logic circuits. We know that everything can be created with AND, NOT, and OR gates. So if a NAND gate can produce these 3 logic gates, then logically a NAND gate can create all these digital logic circuits. So let's see how we can make a NAND gate, or make a NOT gate using just NANDs. Alright, that's simple. Well, I guess it's not. It's simple, but it's not intuitive. You'd have to sit around and think about it for a while. But all you have to do is take a NAND gate and make sure that its signals are the same. Right? So one wire is gonna, just one signal is gonna provide for both in the NAND gate. So if this is a 1, then this is a 0. But if this is a 0, then this is a 1. So there we have a NOT using just an AND gate. Okay, let's take a look at another example. Okay, now let's suppose I want to make an AND gate using this now. That one's going to be very simple now that we have the NOT gate. Because if you recall, a NAND gate is just an AND and a NOT. So if you attach another NOT to it, it's going to cancel out. So, actually, you're going to take a normal NAND gate. You're going to invert it using this NOT gate that we've created. Alright, so using 2 NAND gates, we've created an AND gate, right? And I'm not going to go too in-depth about that one because it's simply a NAND with an inverter. So that's just going to cancel out and make an AND gate. And for the OR gate, what I'm going to do is I'm going to have, what was it? Oh, I remember now. It was one of these knots that we created. Oh, let me draw it better. Right, so we're going to have one there. Another one on the bottom. And those outputs are going to be connected to one more NAND gate. Right, so let's see what happens with that. If this one is 1 and this one is 0, we get 0 here. No, yeah, we get 0 there, 1 there. And 0, 1, that's going to give us a 1. Right? Let's suppose this one was a 1 and this one was also a 1. We get a 0, 0, 0 NANDed with 0 gives you 1. Alright. Say this one is 0, this one is 1. Well, that's going to be the same as last time when this one was 1, this one's 0, so I'm not going to prove that one. But let's say these two are 0. You get a 1 here, a 1 here. 1 NANDed with 1. Remember, that's the only time that an AND becomes 0. So we have proof that this creates an OR gate, this one an AND gate, and this one a NOT gate. So using just the NAND gate, we can create all the logic gates. Alright, my name is Tam N. That was a lesson on NAND and NOR gates. Thank you guys for watching, and I hope to see you next time.